Hello friends, we are back into the physiology classroom and I will continue the discussion on CVS. And in the last video, we have stopped on the xanthines, the mechanism of how an intracellular cyclic AMP can cause the contraction. And we also read about the tea, coffee, the theophyllenes, the xanthines, caffeine, which are affecting the contractility by maintaining the levels of cyclic AMP. Okay. Now, there is another drug in the pharmacology, the drug which is, doing that effect. That is digitalis. See guys, digitalis is basically an inhibitor of sodium, potassium, ATPase. It is an inhibitor of sodium, potassium, ATPase. If it is an inhibitor of sodium, potassium, ATPase, that means it should not allow the sodium potassium pump to throw the sodium out and potassium in. That means this pump, what was the normal function of this pump? Normally it was doing what? Normally it was throwing sodium out, potassium in. Normal function. But if I inhibit this function, what will happen? Sodium intracellular levels of sodium will increase. So let us make a diagram so that life becomes easy. This is one cell. I had a pump on the membrane. I had a pump on this membrane. This was throwing sodium out and bringing potassium in, isn't it? Which sodium, sir? Because after depolarization, you should be able to throw them out. You don't want the maintained levels of sodium inside. This is a normal physiology. Okay, this is the normally what is happening. Normally what is happening? Sodium is going out, potassium is coming in. Okay, through this pump, sodium, potassium, ATPase. But if I inhibit this pump, if I am inhibiting this pump, what will happen? Intracellular sodium levels will increase. Extracellular potassium levels will remain that, whatever they are. And that means if I am increasing the concentration of, listen to the word, more electropositive ion. If I am increasing the concentration of more electropositive ion, that means I am bringing the resting membrane potential more towards the threshold potential. What is the resting membrane potential? It is that potential in which is found in the cell when the cell is not undergoing any depolarization, repolarization. What is the threshold potential? It is that potential that you have to achieve so that you can depolarize the cell, so that you can have that activity. It is that graph I have taught you in the basics. That's why I'm not explaining that again. Okay. When you reach the threshold, for example, I will make like this. These are the two lines. This is the RMP, resting membrane potential, and this is the threshold potential. If you are on this line, let me take a green. If you are on this line, your cell is not doing any work. It is in resting phase. But if your graph, if you increase it, see, I will give you two examples. One example is this. Another example is this. If I make them more closer, this is the RMP. Now threshold potential has come closer to the resting membrane potential. So if I had to climb from resting membrane to threshold, see how much time it would take me to climb. Can we see how much time it would take me to climb this region? But if I have to climb in B case, if I take them as case A and case B, how much time will I take? I will take less time. That means I will have frequently I will depolarize. That means I will achieve these threshold potential very much easily, very much fastly, quickly, as compared to the above where the threshold potential is far from the resting membrane potential. It will take me some time so that I can reach that minus 45. I can reach that minus 45. Isn't it? We have learned it. So minus 70 to minus 45, minus 70, minus 90 to minus 45, that I have taught you already. Okay. Now you tell me, who will determine this? If you have more of the positive charges inside, will the positive charges have the more susceptibility to depolarize the cell? Yes, we have learned it in the physiology. You have to just answer me, okay? Understand it. You can write later on. So when you are reaching the threshold, when you are bringing this threshold potential more nearer to the resting membrane potential, that means the time taken for me to achieve the threshold membrane potential will be very much less. That means I will be depolarizing frequently. I will be depolarizing frequently. Are we clear? So this concept is behind this digitalis. What this digitalis does is, I am increasing the levels of sodium intracellular ion. Intracellular sodium is getting increased. When I increase the intracellular sodium, that means I am bringing the threshold potential more towards the resting membrane potential. Why intracellular sodium ions got increased? Because you were inhibiting the sodium potassium ATPase. That's simple. If you inhibit this pump, you are going to have more inside of sodium ions. Now, if the intracellular concentration of sodium ions is increasing, what will happen? It will actually, to speak in a very more in another way, we can say it opposes the sodium gradient across the membrane from outside to inside the cell. Can I see that? It opposes the gradient. When you are increasing, you are actually opposing the gradient. Sodium gradient is getting opposed. So whatever sodium had to come from outside, it won't come now because you are increasing the intracellular sodium ions. So gradient is lost. The extracellular sodium, you are actually increasing the intracellular sodium. So this intracellular sodium will oppose this positive both. So this gradient will get de-established. This will collapse. We are not letting that gradient to happen. Now, if you decrease the sodium gradient, what you will do? You are actually decreasing the sodium calcium exchanger activity. There is a sodium calcium exchanger. I have taught you in the previous videos. There is a sodium calcium exchanger activity. Sir, in short, what will happen? In short, what will happen if you decrease the activity of sodium calcium exchanger? What is the normal function? What is the normal function of this exchanger? This exchanger was sodium is taken in, calcium is taken out. This exchanger is working. Let me write the first normal function of this exchanger. What is the normal function of sodium calcium exchanger? Let me write it clearly. Okay. The normal function of this is sodium is taken in, calcium taken out by this exchanger, Now, if you are decreasing the exchange of these ions, that will lead to intracellular accumulation of calcium also, isn't it? So these are two connected pathways. One is that sodium potassium ATPase. Another is the connection lies with the sodium calcium exchanger. Are we clear, guys? You increase the intracellular concentration of sodium. When you increase the intracellular concentration of sodium, what will happen? You will decrease the exchange of ions. Normally, they were exchanging the ions. So what will happen in short, sir? In short, there will be intracellular rise of calcium. Now, you also know the story from this. If you are increasing the intracellular calcium, what will happen? Dash. Beautiful answer. You are actually increasing the contractility. So is digitalis having an effect on contractility? That's why we are giving it. By the way, which drugs are inhibiting the myocardial contractility? We have class 1 antiarrhythmics, or we are using those antiarrhythmics. I will be telling you. We have antiarrhythmics. What was digitalis doing? Is it increasing the contractility or decreasing the contractility? Think from the concept in the brain. Is it finally increasing the contractility or decreasing the contractility? It is increasing the contractility. Very nice. Okay. Now listen to me. Which drugs will decrease the contractility? So antiarrhythmics. We have antiarrhythmics in the pharmacology. Like we have quinidine, we have procainamide, we have barbiturates. Okay, barbiturates is also used. Okay. Quinidine, procainamide is a perfectly antiarrhythmics, and barbiturates are we are using for this also for arrhythmia. So this antiarrhythmics, we have what? Quinidine, procainamide. The detailed discussion about these will be in the pharmacology, because you are learning here the physiology only. Okay. So, and what else can it can inhibit? Barbiturates. These are the drugs which can inhibit contractility. Make the note like this, okay? The art of making notes, the art of making notes, that's important. The art how you write is having an impression on your brain. Okay, is this clear, guys? We have talked everything, whatever you need from the physiology of this contractility. Okay, the effects. See where we reached. We started with what? We started with the factors which are affecting the what? Cardiac output, and we said, let me make you oriented again. We said that cardiac output is having the equation of stroke volume into heart rate, and that stroke volume we took the component in the previous videos. How we started with cardiac output is equal to stroke volume into heart rate. Be oriented first, and we said if these are the factors, I should directly describe them. So stroke volume, I told you stroke volume is being it depends on three factors. I told you it's preload. I told you it is, yes, myocardial contractility or inotropic state. And now we are going to study the afterload. Can we understand how we are oriented? Then we will be going for heart rate. See, orientation is important. Medical student is, so Glasgow comma, we have a GCS scale in the emergency. That is Glasgow comma scale. We are using the motor response, eye movements, consciousness level. We are checking the consciousness level. The GCS scale of the perfect medical student, we have for 50. Why? Because we need to remain oriented about everything. That's what makes us different from the other communities, other society, professionals. Why? We need to remain alert at every time. In the emergency, even when we are on a 24th hour of our duty, we still can function like you bring any emergency and we will. You have to prepare yourself like that. That can only happen if you have studied in an oriented way. Your brain will think in that way. See, if I ask you directly, tell me digitalis what it does. Now, some people, what they do, they directly jump to the answer of contractility. It increases the contractility. But you as a medical student in the initial years of the medical school, how you think? You will say, yeah, digitalis. Let me first think. You have to think like this, then you have to answer. That's what concept is. Digitalis is inhibiting the sodium potassium. That is in turn inhibiting that sodium, increasing the concentration of calcium. That means that intracellular calcium levels will cause the increase in the contractility. Then you will answer me, sir, it increases the contractility. That is how beautifully you can explain everything. If you are not doing this, then you will do wrong answers in the exam. You have to think yourself, yeah, it is inhibiting. Okay, done, finished. It just takes 10 seconds. Just takes 10 seconds. And you have 40 seconds in the exam. You have 40 seconds for a question. 10-15 seconds you will take in thinking. 2 seconds, 5 seconds you will take in searching what I have to answer. And then next 10 seconds you can take. Is it clear, friends? So this is how you have to train your brain. You have to train your brain. Brain training. That's what I am trying to do here in the class also. Okay. Now preload, inotropic state, afterload. Now I take, this is done. This is done. Now I go to the afterload, guys. Okay. Not much about this afterload, but yeah, I will try to make something, some important points I want to discuss here. See, afterload is what? What is afterload? Anabum, sodium. Yeah, very nice. Okay, you can make like this. Okay, you can make like this. Okay, I draw this for you. You can draw it. I think you can draw it. Okay, you can draw it. Sodium, potassium, you have inhibited. Then you are inhibiting this. You are increasing the intracellular sodium. You are diminishing the gradient. You are decreasing the gradient. And then you are increasing the calcium levels. I can write like this: intracellularly calcium levels is increasing. That will cause increase in contractility. This is how you can understand. Simple, one line. Change your life. Okay. Now I take the afterload, guys. Yes, it is the resistance in the vessel. Okay. To be very much precise, I would say afterload is basically the pressure or resistance. It is the pressure, let me write, it is the pressure or resistance against, listen to my word, against which the ventricles must pump the blood. against which the ventricles must pump the blood. Must pump the blood. Against which the ventricles must pump the blood. Okay, ventricles must pump the blood. That means this resistance he is talking about the aorta and towards the peripheral vesicles. Because who is pumping? Ventricle is pumping. Who is pumping? Ventricle is pumping. Right ventricle, left ventricle. Right ventricle pumping against what dash? Against what? This is acting as a resistance. See, I told you in the beginning of hemodynamics lecture, these are all resistances. Whatever you are connecting, that will be showing its resistance to flow. Little or more resistance is there. Resistance is there. So this is for the PV. Very nice. This is for the PA. This is for the PA, pulmonary artery. And this is for the aorta. This is for the aorta. And aorta is connected to systemic vessels. Aorta is supplying through systemic vessels. These are acting as a resistance. So that means afterload is telling me that what is the status of the blood or what is the systemic blood pressure. Can I write SBP? Yes, sir. You have taught us in the beginning. SBP is basically the TPR, total peripheral resistance or systemic vascular resistance or systemic blood pressure. Are we clear, guys? So that means these peripheral vessels will be determining the systolic BP, and this is in turn determining the afterload. That means the blood column which is present in this vessels, that will actually make a load here. That is actually acting as a definitely stroke volume should depend on this. Whatever the status of blood column is present in this vessel, these all constitution, whatever is there, that will actually determine the stroke volume also. So stroke volume is dependent on what? On the afterload. So that means that, did you understood the definition what I read? It's against pressure or resistance against which the ventricles must pump. So what is the ventricle pumping against? It is pumping this resistance. What was preload? Preload was the column of blood against which it was pumping. What was the preload, guys? Preload was, the definition of preload was, it is the degree of tension or load on the ventricular muscle when it begins to contract. When it begins to contract, we say preload. When it is contracting, when it has to contract, against what resistance, that will be determining the afterload. That means, can I say any obstruction in the aorta? Let me make it with color. Any obstruction in the aorta, will it increase the afterload or not? Any resistance in the aorta? Beautiful answer. It will actually resist the blood column here. So that's why, what a beautiful concept. Any obstruction you are doing to the ventricular outflow, any obstruction. Very nice. Yeah, this is also the same definition. Okay, very nice. Okay, so against the ventricle which must pump, it's okay. Now I am telling you, if this is the aorta, will I increase the afterload or decrease the afterload? If you are causing narrowing of this area, will you increase the afterload or decrease the afterload? You are increasing the afterload. Can I give a clinical correlation here? Can I say in patients of aortic stenosis, please write, in patients of aortic stenosis, what happens in aortic stenosis? This is the aorta and the aortic valves become narrow. They cause a narrowing. The stenosis happens, narrowing happens. Will it increase afterload or preload? Now people start speaking preload. I don't know how preload will increase. You are yourself telling, isn't it? Very nice. So it's afterload against which you have to, which is behaving as a resistance. Okay, this narrow is behaving as an increased, the resistance is accentuated. That's why. Aortic valve, stenotic aortic valve. Okay. Now, I will be telling you some other things. Okay. Can I say if someone is having hypertension? Hypertension means, for example, I am having constriction of these vessels, HTN. If there is systemic hypertension, that is blood pressure is increasing. Is it increasing the preload or afterload? Beautiful answer. It will increase the afterload. Are we clear how things are working? Will it increase the workload on the heart? Will it increase the workload on the heart? Does the heart have to pump so hardly, have to work so hard to send the blood to the systemic vasculature? It's a beautiful answer. Can we understand? Can we understand, guys? Very nice. So that means stroke work will increase. Okay. I have to do more mechanical work. With each contraction, I have to do more mechanical work, isn't it? Okay. If I have to maintain a constant stroke volume in the afterload, do I have to increase or not? If I want to increase, you want 100 ml of blood, for example. You want 100 ml of blood. This 100 ml of blood, your body, your heart is so kind and nice to you. He wants to keep that 100 ml of blood. Even still, you are increasing the BP. You are increasing the afterload by any cause. Still, you are maintaining this 100 ml. So are you doing the more? Do you have to do more work to do this? Yes, sir. So that is what stroke work is. What is the meaning of stroke work? Who can tell us the definition of stroke work, guys? These are some important things you should have on your fingertips. Let me tell you the definition. Stroke work is basically, if I make it easy for you, it is basically a measurement. It is telling me how much mechanical work has been performed. Can you understand the mechanical work? Yes, you can understand mechanical. Mechanical work which has been performed by the ventricle with each contraction. What is the meaning? How much mechanical work has the ventricle done with each contraction? Mechanical work with each contraction. Are we clear, guys? So this is the stroke work. And volume you can understand. Volume I have taught you. Yeah. So that means who will affect this stroke work? Let me give you a correlation here. Okay, let me correlate it. Okay, friends, I will correlate for you. Stroke work. This stroke work will increase by, you want to give a constant stroke volume in spite of increasing the afterload. If your afterload is increasing, I can now think, you can also think, sir, afterload increase means I have to think about the vessels and aorta. So if I increase that resistance, be by any vasoconstriction, anything, any obstruction, aortic valve stenosis, that means that will increase the stroke work. Because why it is increasing the stroke work? It wants to maintain that stroke volume. It wants to increase that blood flow through that vessel so that it can send that blood to the peripheral tissues. Okay. Basically, this stroke work is made up of two things. I used to write when I used in my first year, how I used to read it. I used to remember it. There was something in the book I remember. They used to say it is made up of two components. They said it is made up of two components. There are two components of stroke work. Okay, let me write it. One they used to write, one is called pressure volume work. Let me write it for you. Pressure volume work. And another was kinetic energy work. What? Kinetic energy work. That's right. Kinetic energy work. So one is pressure volume work, another is kinetic energy work. Okay. Pressure volume work, to make life easy, just understand like this. First, let me tell it what it is. Pressure volume work is that type of a work which is done to push the stroke volume into any high pressure arterial system. What did I say? I said it is the work. First you have to say what it is. It is work, is it force, is it what? It is a work which is being done to push the stroke volume into the high pressure arterial system. Let me write it for you. So it is the work. First you should say it is a work which is being done to push the stroke volume into the high, this is important statement, high pressure arterial system. You should write arterial system. If the arterial, this is not atria. Please don't confuse this atria with artery. Okay, these are two different things. Atria is about the heart. No, I'm talking about arterial system. Okay, friends. So this arterial system, then what it will be equal to? Can I say stroke volume is equal to this pressure volume work is equal to the systemic arterial pressure multiplied by the stroke volume? Can I say P into SV is the pressure volume work? See, it's so easy. Can I say it is equal to work? See, if I go into the physics, what was the physics saying? Work is equal to force into displacement. F factor dot ds factor, isn't it? F factor was the force and S was the, what was S? Displacement. So how much force and displacement, or you used to write F factor dot dx factor, isn't it? The displacement in your, in the long time back. Okay, I remember this equation. So same equation has been used here. Whatever pressure volume work you want to do, multiply the pressure with that stroke volume. That is your pressure volume work. So will this stroke pressure, will the pressure govern your stroke volume? Yes, sir, definitely. That's why we are saying it is the work which is used to push the stroke volume into the high pressure arterial system. And it will be multiplied by the two quantities. This two multiplication will tell you how much pressure volume work you have done. Okay. And remember this thing, this is the primary component. You should remember this. It is the primary component of stroke work. Stroke work. What was stroke work? Again I speak. What was stroke work, guys? Stroke work was the amount of mechanical work which you were doing with each contraction. But who is forming the main component? It is this pressure volume work which will be doing that stroke work. Are we clear? It is the primary component, guys. That means what do you mean by primary component? That is, it is major component. That is, it is the main component. While as if I take the kinetic work, it is a minor component. Kinetic energy work is a minor component. Let me write that. Kinetic energy work, it was so difficult for me when I was reading this from the, and standard textbooks are very nice and beautiful textbooks like Guyton, Ganong, I was reading those. So I was getting confused with this system, what is happening. Then I understood it with more readings, 5-10 times I read it and then I have understood it, what it means. And when we were reading the pathology, the diseases, then I took the physiology also and then I understood what the thing is happening. So I have tried to make it so simple. I think it's not having there is no difficulty in understanding. Otherwise in the book you will get lost. So that's why I'm guiding you here. Okay. So this kinetic energy work is basically, what is the kinetic energy work? It is again the work which is being done by the ventricular contraction. And that work is helping the blood to get ejected at a certain velocity. What did I say? I said it is the work. First you should say it is a work. It is a work which is being done by what? Which is done by this work. Basically it's not the work which is done, it is basically conveyed. Let me write that. Work which is conveyed. I will make you understand this, the diagram also. Which is conveyed. Do we understand the word conveyed? Yeah. Conveyed by ventricular contraction. Ventricular contraction. Now listen. So that we can move the ejected blood. So that we can move the blood which you are ejecting, that should move. So that ejected blood should move. So that this is why kinetic energy work is happening. Okay. So contraction, so that we can what to write? So that we can move the ejected blood. Why do you want to move the ejected blood? For attaining a certain velocity. Ejected blood at a certain velocity. Okay. We will understand. So for example, this is your left ventricle and this is your aorta. You have ejected, you have done the pressure volume work. And there is some blood which is moving because of, by virtue of motion of the blood, you are doing some work. and that too is being supplied by the ventricle. That is actually that continuation of that force which has been generated by the ventricle. Are we able to understand? You need to bring your brain to that minor imaginative level. Okay, so again I will draw it for you. So the ventricle has contracted. Ventricle has contracted. If ventricle is contracted, what has happened? This blood volume of blood is getting through this. Now they are moving, and that movement has been actually done by the pressure volume work, which is basically the push, the stroke volume, to push that stroke volume into the arterial system. So the movement of this blood is basically doing a kinetic energy work, and that is actually being supplied by at the back that is being supplied by what? Are we able to understand this basic concept? So it is the work which is being actually conveyed, which is being supplied by the ventricular contraction. So it all depends on the pressure volume work. So that's why we say under normal circumstances, our kinetic energy work is no, it's not that major component for the stroke work. Are we clear, friends? So these, I think, are the important things which you need to study about this thing. No need to go into something in detail at this MBBS level. You need to understand this. Okay. So I hope you have understood this, what I mean by this, all this. Yeah. So suddenly we went to something else. So yeah, afterload. So we were saying about the afterload. So what was the afterload? We said that it is basically that resistance, that pressure which is being generated by that arterial system against which the heart has to push, heart must pump the blood. Okay. So afterload is basically I want to explain 2 or 3 things and then we finish the chapter. Okay, this topic. Okay, the stroke volume factors. So that means it is to take it easy, resistance. So resistance from vessels, afterload. Okay, resistance for resistance. So can I say peripheral resistance? Let me write it for you. Peripheral resistance is equal to afterload. Make life easy. It is equal to afterload. Can I say cardiac output is inversely proportional to afterload? So easy, sir. If this is a vessel and this is a ventricle, sir, if I narrow this, what will happen? Afterload will increase. Will I eject more blood or less blood? Less blood. So cardiac output will become less. Cardiac output will become less if you increase the afterload. Is it clear, friends? If you increase the total peripheral resistance by any cause, vasoconstrictive action, any sort of a tumor, pheochromocytoma, anything, that will decrease the cardiac output. And if you try to vasodilate, if you give an arteriolodilator, any dilator, vasodilator, what will happen? Resistance will decrease. That means blood will move more like a river, isn't it? Suddenly you have opened, you have dilated the vessel and then blood will rush out. Okay. And remember, this cardiac output change, which is happening without the change in the ventricle. So in this afterload, so that means this effect, which we said last time also, that the cardiac output is changing, but you are not doing anything with the ventricular muscle length. The ventricular muscle length, this ventricular muscle length is not changing, but you are increasing the cardiac output. This is called homometric autoregulation, or it was also known as NRAP effect. What effect? NRAP effect. NRAP effect is also known as homometric autoregulation. Let me write it clearly. Homometric autoregulation. Okay, easy. That means afterload is dependent on what factors? Now going to afterload, they are going inside. So afterload depends on two factors. It depends. Number 1, vessel diameter. Second thing, viscosity of blood. In other ways, we used to say there are We used to say vessel diameter is a vascular hindrance to afterload. Viscosity of blood is a hematological hindrance. When we used to say vessel diameter is equal to, in case of afterload, we used to speak like this: vessel diameter is a vascular hindrance, not resistance, vascular hindrance to afterload. And viscosity of blood is hematological hindrance. Can we understand this? So it is dependent on two factors, vessel diameter and viscosity. What is vessel diameter? That means if you decrease the vessel diameter, that will increase the resistance. That will decrease the stroke volume. That means in vasodilatation, stroke volume should increase because afterload is decreasing. So that means it's like this. If you increase the peripheral vascular resistance, you will be basically, who is increasing the total peripheral resistance? It is by vessel diameter. If you decrease the vessel diameter, you make it more small, what will happen? Resistance will increase. Resistance will increase. That means stroke volume will decrease. Now if I increase the vessel diameter, what will happen? Peripheral resistance will go down. Resistance will decrease. That means stroke volume will go up. This is what you have to write in your copy, nothing else. Don't try to write a new book, okay? We don't have time in the end to revise these things. Revision is important. Okay, guys. Now going to the viscosity. Under viscosity heading, what you will write? In the viscosity, that means viscosity means the degree of what? Flow of that liquid. That means it will depend on the constituents of the things inside it. It will depend on the constituents of the blood. Whatever is in the blood, is it more liquid? So that means if you increase the viscosity, like this I will say, if you increase the cells, if you increase the cellular components of the blood, okay, what will happen? You are increasing the viscosity. I have taught you in the previous lecture, just connecting it. So if you increase the blood cells, in which case is blood cells increasing in which disease? Polycythemia. What will happen? Increase in polycythemia, what will happen? You are increasing the viscosity. And this will again increase the peripheral resistance, isn't it? The flow is so much slow. That resistance is more. You have to drag it through the vessel like this. You have to drag it. My God, you have to drag this blood. That is, resistance will increase. What will decrease then? Cardiac output will decrease. Now, this was one disease, easy disease. Now, what happens in anemia? What is anemia? Either decrease in the hemoglobin or decrease in the RBC. You are decreasing the cellular component. If you decrease the cellular component, what will happen? You are actually decreasing the resistance. Why? The fluid is becoming more what? Viscosity is decreasing. Increasing or decreasing? Viscosity is decreasing. That means it is more of a fluidy. The blood is more of a fluidy thing. More fluid dynamics. What will happen? This fluidy thing or decreased viscosity will decrease the peripheral resistance. If this decreases, what will happen? You will be having increased cardiac output because viscosity has decreased. Viscosity decreased, that's why cardiac output increased. In polycythemia, resistance increased. Resistance increased, that's why cardiac output decreased. Okay, are we clear, guys? So in the next video, I hope that you have enjoyed. We have finished the factors which are actually governing this cardiac output. In the next video, we'll be continuing with the same topic. Okay, and then we will land in some graphical matter. Okay, graphical thing. Okay, anemia, cardiac output will increase. Okay, I have written already, guys. Okay, cardiac output increase in anemia, decreases in polycythemia. can be now any polycythemia vera or any condition. Okay. So I hope you've enjoyed this discussion. Please keep revising and please keep finishing all the videos. Read the previous videos also if you haven't watched them. See you all next time. Take care. Bye-bye.